We are going to design a toilet today. Actually, no, not a toilet. We're going to design the control mechanism using the state machine theory that we talked about in the previous lessons. So what we've got is, and you know, in this day and age when we don't want to touch anything, these touchless flushing toilets, really, you know, they're everywhere. So how do they work? Well, you know, you walk up to the toilet and there's a small device in there, this rangefinder, which determines whether or not somebody is in front of the toilet. And so we're going to have a system that looks like this. We've got an input, which we're going to call P. P for present. In other words, P equals 0, no one is present. And P equals 1, someone is present. And we're going to look at this idea that, well, in use, not in use, in use, okay? And there's going to be an output. And I'm not an expert in plumbing, but I do know that whenever you flush a toilet, you don't have to stand there and hold the button down as long as it's flushing. You don't take care of the timing. All you do is you just simply press it and go. And so we are going to have an output, F. So F equals 0, and that's not flushing. And then F equals 1 is flushing. Now, Now, we're not going to have some sort of a timer like we did with the traffic signal. All we're going to simply do is just have it, you know, just a pulse for 1 clock period. We're done. All right. Well, let's see if we can't do this. And believe it or not, there is a reason why I picked this particular topic. Now, as I said, most all state machines need to have some identifier which talks about, or which identifies where we're going to start our system. And kind of imagine this, you know, whenever you first power up this system, or whenever, if maybe it's hardwired to the electricity in the building, and whenever the power goes out, when the power comes back up, what state do you want all of the toilets to be in? Well, probably wouldn't be very good to have them all flushing at the same time. So what I'm going to do is I'm going to draw a horizontal bar through this state identifier, this vertex. Remember, these vertices in graph theory identify the individual states. And in the lower half, what I'm going to do is tell exactly what state. Remember, this is a Moore machine. The output depends only on the state. The flushing, I'm going to have this particular reset state being F equals 0. We're not flushing. Now, more than likely, nobody is in front of the toilet whenever it first powers up too. And so I'm going to call this state idle. All right. So whenever everything comes up, we're going to assume that it's not been in use, that it's not supposed to be flushing. It's just hanging out, you know, being a toilet. Right? Okay. Now, remember, what we need now is an edge, a transition for each one of the values of our input. Now, we just have one input, P, and P can be equal to 0 or 1. So there need to be two transitions. One transition which says what happens whenever no one is present and what happens when someone is present. Okay. Now, coming out of idle, if no one is present, P equals 0, we pretty much want to continue to be idle, right? And so as long as no one comes up to the toilet, we want to continue to stay in this idle state. And so as long as that clock ticks on and ticks on and ticks on, we're just going to stay idle until somebody comes up to use the facilities. If somebody comes up to use the facilities, P equals 1, what do we want to do? Well, we want to transition to a new state, and this new state is going to be in use, okay? So I'm going to have a new state here. I'm going to call this new state in use, all right? Now, do we want it flushing while it's in use? Probably not. probably not an appropriate thing to have the toilet flushing whenever somebody first starts using it. So we are also going to have f equal to 0 for this in-use state. So when somebody comes up to use the toilet, we are going to clock tick. We're going to go ahead and go to the in-use state. Now, one of the things that we talked about in an earlier lesson was this idea of how fast the clock needs to be ticking along. If the clock is moving too slowly, then, for example, if the clock ticked once every minute, that's a pretty slow clock. But if it clocked once every minute, it's possible it may miss somebody coming up to the toilet. But we also don't really want it to go, in the case of the toilet, we don't want it to go too fast because we are going to have a state where it's flushing. And that state where it's flushing, we need to just stay in that state long enough so that it will activate all the plumbing in order to clean out, well, you know. All right. Now, we've stayed idle. Nobody's using the facilities. Somebody comes and uses the facility, so we're in use. Now, as long as that person is there, we want to stay in use, right? So we're going to have a P equals 1 transition. Every single P equals 1, actually, in fact, think about it this way. Anytime somebody is present, we should be in the in-use case. So you think about it, all the P equal 1s should end up in that state, right? But what about P equals 0? P equals 0. If P equals 0, do we want to go back to idle? No, we've got to flush this toilet, right? And so we need to have some sort of an intermediate state. And we'll call this one flush. And that one is where we're going to set f equal to 1. All right? And that occurs when the facility has been in use and then the person walks away. All right? So I've got 2 transitions out of idle for P equals 0, P equals 1. I've got 2 transitions out of in use. I don't have any of my transitions out of flush. All right? Now, I'm only going to worry about staying in flush for 1 clock period. Like I said, let's just make it so that the clock period is long enough so that we can stay in flush long enough to get the plumbing to work. All right? But get a clock pulse after this, we have to decide what to do. So if P equals 0, that means, well, it was in use, we came to flush, P equals 0 said, nobody's come back yet. There's not a line, all right? And so if nobody's come back, then P equals 0, we should probably just go back to idle, to waiting to be used, right? But assume there's a line. If there's a line, P equals 0, we flushed, and then if P equals 1, that means somebody came up to use the facilities immediately after, we're back in use. And we've got this, once again, this idea that all P equal 1s lead to in use. All right? Wow. Looks like we're done. In fact, let's think about this. How do we know if we're done? How do we know if that's a complete state diagram? Well, let's take a second, step back from this state diagram and talk about the ways we would identify any particular errors that might occur in a state diagram or might be present in a state diagram. And there's 2 in particular that I'm concerned about. The first one is every single state must have, and this is for a Moore machine, every single state must have a transition, an edge out of it for all of the possible input values. So if there are 2 different input ways that the inputs could be, P equals 0, P equals 1, there needs to be a P equals 0 and a P equals 1 out of every single state. And there is for this case. P equals 0, P equals 1, P equals 0, P equals 1, P equals 0, P equals 1. If there were 2 inputs to this system, then there are 4 possible patterns of 1s and 0s, and I'd need to have 4 transitions out of every state to represent every way that we can have an input. All right? Now, there's another possible way that an error could occur. And this is really hard to create this error if you're developing the state diagram the way we've been developing them, where we simply create states as we need them. But if you've got a bunch of states and you start connecting them with the transitions, it's possible that you've created a state that there's no way to get to it. All right. Now, in general, the easiest way to identify a state that's impossible to get to is it doesn't have any transitions coming into it. It's got an in count, the term used from graph theory, an in count of 0. And so I've got, well, and by the way, this reset transition, that's an in count of 1. Because if you think about it, for example, if you've got a splash screen that your software goes through whenever it first fires up, you shouldn't from your software come back to that splash screen. It only comes in during a reset condition. So reset would be considered an in count. So for this circle, this state right here, I've got an in count of 1, 2, 3. That's okay. An in count of 1, 2, 3, that's okay. And by the way, this in count really shouldn't count because you need to get to that state before this transition can take place. And then this one, we can get to it from the state in use, so we can also get to that state. So all of those states up there, those are possible to get to. Now, the next thing, so we've done our overall system design, we've created our state diagram. What was the next step? Well, it turned out the next step was quite trivial. The next step was just number the states. Because remember, each one of these states, whether we're going to know which one of these states we're in by recognizing what memory, what's in our memory. The memory is going to contain the current state. And since memory is made up of patterns of 1s and 0s, we have to figure out which patterns of 1s and 0s each one of those guys represents. So I'm going to just do it the way we usually do it. I'm just going to go counterclockwise, or go clockwise. This is state 0, this is state 1, this is state 2. Now, we need to do this in binary. And the reason we need to do this in binary is we need to recognize exactly how many flip-flops, we need in order to store the current state. You look at the largest number is 2. Convert that to binary. A 2 in binary is equal to 1, 0. That means that our state is going to be stored in 2 bits. And I'm going to label these like we have. The most significant one I'm going to make S1. The least significant one I'm going to make S0. So we'll convert the rest of these guys to binary, 2 bits. All right. Now, that means that a 0, 0 in the flip-flops for S1 and S0 say that we're in idle. A 0, 1 says we're in use. A 1, 0 says we're flushing. Okay. All right. Now, the next step was to make our logic. There was actually 2 truth tables that we needed to create. The 2 truth tables, one of them associated the state with the output, and that was our output truth table. And this one's going to be quite simple. We'll just simply say output truth table. And it has its inputs S1, S0, and its output was F. There are 4 possible patterns of 1s and 0s for our state bits. So remember, the output simply maps the state to the output. That's all it's doing. And this is the way it is with a Moore machine. Now, in state 0, 0, we're not flushing. In state 0, 1, we're not flushing. In state 1, 0, we're flushing. In state 1, 1, there is no state 1, 1, is there? Now, if you remember back whenever we first introduced this idea of Karnaugh maps, we talked about the don't care. Well, hopefully, we should never go to that state, right? Unless there's some sort of a glitch, some sort of maybe a stray gamma ray hit one of our flip-flops and changed it to a 1, to change both of them to a 1, 1. We really are not going to have any need to worry about this state. We'll make sure we can get out of it if we accidentally do get into it, if through some glitch we accidentally get into state 1, 1. But that's a job for our output truth table. Our next state truth table. All right, so what does this look like? Well, the output, we could do a little Karnaugh map. Now, a Karnaugh map for a 2-input truth table, just a little 2x2 square there. So 0, 0 has a 0, 0, 1 has a 0, 1, 0 has a 1, and 1, 1 has an X. Now, if you recall, those X's are wildcards. You can make them whatever you want to make in order to make a simpler expression. So we're going to make that X a 1 so we can have a larger rectangle. And it turns out that this Karnaugh map says that as long as F follows S1, we're going to have a successful output. So I'm going to go ahead and we'll just, I need a little bit more room up here. I'm just simply going to say F is equal to S1. And so this expression right here is our output circuit for this state machine. All right? All right. Let's clear some space, make the next state truth table. All right, let's look at our next state truth table. Now, our next state truth table is going to take the current state, S1, S0, and the input, P. And it's going to tell us what the output is, what the next, I keep using that, sorry about that. It's going to tell us what the next state is going to be. So that's our S1 prime, S0 prime. So for whatever the current state is, all right, plus our input, that is going to tell us what our, make a little bit more, I needed more room there. It's going to tell us what our next state is going to be. All right. Now with 3 inputs, I've got 8 possible patterns of 1s and 0s. All right. And really, it's just a matter of saying, when I'm in this state and the input's that, where am I headed? So when I'm in 0, 0, when I'm in state 0, 0, and P is equal to a 0, I'm headed back to state 0, 0. So as long as I'm in state 0, 0 and P equals 0, and I keep getting those clock ticks, I'm going to stay in state 0, 0. Now, I'm in state 0, 1 and P is equal to a 1. State 0, 0, P is equal to a 1. I'm headed off to state 0, 1. Right. If I'm in state 0, 1, state 0, 1. So, and by the way, these first 2 rows take care of these first 2 transitions. So I'm in state 0, 0, state 0, 1. What happens when P is equal to 0? What happens when P is equal to a 1? That's these 2 transitions. So I'm in state 0, 1. P is equal to a 0. I'm in state 0, 1. P is equal to a 0. I'm coming down here to state 1, 0. When I'm in state 0, 1, and P is equal to a 1, I stay in state 0, 1. So that 0, 1, P equals 1, stay in 0, 1. Now I'm in state 1, 0. State 1, 0. If P equals a 0, then I'm headed back to state 0, 0. If I'm in state 1, 0, and P equals a 1, I'm headed up to state 0, 1. All right. And then these last 2 states, or say last 2 rows, say what happens if I'm in state 1, 1? Well, remember, there is no state 1, 1. So these guys are going to be don't cares, both of them. Now, the deal is that after I figure out my expressions, I'm going to leave this truth table up here. I'm going to figure out exactly what those guys are actually equal to in our expressions so that I can identify if we accidentally get into one of those conditions, is if we accidentally get into a state 1, 1, will it come out or will it get stuck there? Because remember, in our output, this expression right here, we decided that we were going to go ahead and flush if we accidentally ever got into that alien state. Well, let's see if it's okay to get in that alien state. And by the way, this state diagram is no longer needed, because all the information from this state diagram is actually taken care of. We had the output truth table, which took care of the outputs associated with each state. And then we've got the next state truth table, which takes care of all the transitions. So we actually do not need this state diagram anymore. So let's do the Karnaugh maps for this guy. We'll do one for S1. So we've got a Karnaugh map for S1. And, excuse me, S1 prime. We're doing this column right here. And that's going to take as its inputs S1 and S0 and P. So we'll go ahead and use our gray code to number the rows. And then I've got S0 prime. And we'll make the Karnaugh map for this guy. And that also has as its inputs S1 and S0 and P. We'll do our gray code to number the rows, and the columns are numbered for the two values for P. All right, so let's transfer this 3-input truth table to these 3-input Karnaugh maps. So in this cell right here, this top left cell, 0, 0, 0, we're headed to state 0, 0. Next cell, 0, 0, 1, we're headed to state 0, 1. This cell right here, 0, 1, 0, 0, 1, 0, we're headed to state 1, 0. Next cell, this cell right here, 0, 1, 1, 0, 1, 1, we're headed to state 0, 1. And by the way, remember, all of this is on the Karnaugh map lesson, so if you've forgotten how to do the transfer for the Karnaugh maps, just head back to that lesson. Okay, so we filled out our Karnaugh maps. These two Karnaugh maps actually turned out to be pretty nice. It looks like if we use our X's as wildcards, okay, we've actually got some pretty decent rectangles there, right? Now, by doing this, what I'm saying is that this cell right here, the one that is identified by 110, that after we do our circuitry, is going to be a 1 and a 0. So this guy right here, it actually turns into a 1 and a 0. For this cell right here, the one that represents the row in the truth table, 111, that cell, we want our wild card to be a 0. This cell, we want our wild card to be a 1. And so that means this bottom cell is going to state 0, 1. Now, the thing I wanted to show you here was that the Karnaugh map will identify what we want these don't cares to be. And I wanted to make sure I didn't accidentally get stuck in one of these states. If I was stuck in, for example, if this ended up being 1, 1, then as long as nobody was present, every clock pulse, I was just gonna stay locked in 1, 1. And remember, the output said that I was gonna be flushing during state 1, 1. So I wanna make sure that I can get out of that state. And it turns out with a clock pulse, if I accidentally get into this state through some sort of a circuit error, then I'm actually, if nobody is there, I'm going to go to state 1, 0, which is my flushing state. So remember this was idle, this was in use, these were flushing, or flush. And so what's going to happen is that if nobody is there, it's going to jump into flush and we'll go back into the normal state operation. If we got into state 1, 1 and somebody was there, it'll jump instead up to in use. So that looks okay. So we'll go ahead and stay with those rectangles. Now, what is that going to give us for expressions? Well, S1 prime is going to be equal to, if P is 0, and S0 is 1. So this is S0 P bar, inverted P, okay? This one right here, as long as P is equal to a 1, S0 prime is going to be equal to a 1. So S0 prime is just equal to P. All right? I think that's right. All right, so let's draw our circuit. But before we do, let's make some room. Now remember, our state machine is divided into 3 pieces, 3 sections. In the middle we have memory. Going from our memory to our output, which in this case is going to be F, we have our output logic. And then going from our input, P, to the input of our memory, this is going to be our next state logic. All right, so let's go ahead and draw this up. First of all, we already decided we have two memory cells. All right, we have D, clock, and Q for each one of these, D, clock, and Q. The output Q, this is S1 and S0. And then coming back in on this side, we've got, going into D, we've got S1 prime and S0 prime. And then remember, we've got this one clock, which keeps everything in lockstep. So I'm going to connect the clocks together. And this is just going to be the system clock, what's just keeping us going from state to state to state. All right. Now, the output logic. We've already decided the output logic is just equal to S1. So all I have to do is actually take S1 and run it to my output, F. Now, the input, the next state logic, the input is actually being combined with both of the state bits. So I'm going to take both of the state bits and bring them over to the input side. So our input expressions all depend on not only the input to the system, but also the current state. Now, they're actually pretty simple. S0 prime, for example, we just simply connect P directly to S0 prime. If P is a 0, S0 prime is going to be a 0. That means our next state, if P is equal to a 0, our next state is going to have 0 as its least significant bit. The next state S1 prime bit. S1 prime is equal to the AND, the product of S0 ANDed with P bar. And there's our circuit. Now, there's one thing that you might be a little bit concerned about, and that's that S1 is not being used to figure out the next state. Maybe we need to maybe S1 wasn't necessary. No, it was necessary. First of all, one of the reasons we can say it's necessary is that there are 3 states, and in order to uniquely identify 3 states, you need 2 bits. But S1 also is important because it's the one that's defining what the output F is. Another way you could look at this is that S1 is just not needed in order to determine what the next state we're going to is. But S1 is vital in terms of the operation of our toilet. All right? There you go. Didn't think it would be that easy, did you? Pretty simple circuit.